What's on screen are terms which are the ingredients of modern physics, in the same way that you have flour, sugar, eggs, butter, and milk to form a cake. The following are ingredients of the universe as we know it. The universe combines these all, but we don't know how. And further, we don't know of a source that could give rise to all of these. Is there something like the 4 simple base pairs of DNA that give rise to the protein bonanza that we call life? Let me go through these one by one. Firstly, we have Einstein. Now, specifically, this term represents the Ricci curvature tensor, defined as the contraction of the Riemann tensor. Most people don't realize that this is quite odd, as the Riemann tensor has its antisymmetry in the last 2 factors coming from it being a 2 form, whereas the first 2 factors have antisymmetry coming from the Lie algebra, which is actually after you pull down the I with the metric. More on this later, but intuitively, the Ricci scalar measures how volume changes in a curved spacetime, capturing the gravitational effects of matter. The next is Yang-Mills Maxwell, and this term is the Yang-Mills action for gauge fields, where Fa is the field strength, also known as the curvature, associated with the gauge connection A, given by this formula here. And this inner product is something called the killing form on the Lie algebra of the gauge group. Intuitively, this term represents the energy stored in the gauge fields. The next term describes the action for fermionic fields, psi and psi bar, where psi bar is the Dirac adjoint of psi, and this D with a slash is the Dirac operator coupled to the gauge connection. The gamma matrices here satisfy the Clifford algebra, and this guy describes how particles like electrons and quarks move and interact with gauge fields within spacetime. Confusingly, this psi here isn't the same psi as a wave function. This is just one of the many ambiguities in physics. You're just going to have to get used to it. The next is Higgs, and this governs the dynamics of the Higgs field, and through the potential here, it gives mass to gauge bosons like the W and Z ones via spontaneous symmetry breaking when this Higgs field acquires a vacuum expectation value. And this next factor here is when the Higgs field acquires a VEV, a vacuum expectation value, this time giving rise to mass for fermions, which is in proportion to the strength of the Yukawa coupling. At this point, don't worry if you're confused. Again, this video is meant to be watched and rewatched, and furthermore, this is standard physics, so nothing here is specific to geometric unity. All of this will make sense, and I'll explain and re-explain, just keep watching. Now, this next term, spin 1,3, I could have also said SL2C technically, which is the double cover of the proper orthochronous Lorentz group SO plus 1, 3. Which is actually necessary for representing spinor fields, and anyhow, this is what allows us to correctly describe particles with half-integer spins. Then there's this, which you hear of plenty, SU3 cross SU2 cross U1. This product group is the gauge symmetry group of the standard model, where roughly speaking, SU3 corresponds to the strong force, also known as quantum chromodynamics, and SU2 corresponds to the weak force, technically isospin, and U1 corresponds to electromagnetism, though technically hypercharge. Next, we have the family quantum numbers. These will be outlined later in this talk, but intuitively speaking, this space encodes all the intrinsic properties that distinguish different types of particles within a particular generation. Now, next, speaking of these generations, this denotes that there are 3 generations of matter. Now, some people call them 3 families. I've also heard it called 3 flavors of matter, confusingly again. This field here, psi, can be decomposed as follows. That's what this symbol here means, which represents these 3 generations or families or flavors or whatever you call it. This accounts for the existence of particles like the electron, the muon, and the tau, which are all similar in behavior, but they differ in mass. And lastly, please don't make me pronounce these, the CKM Matrix explains why quarks can change types or flavors during weak decays, leading to phenomena like the decay of a strange quark into an up quark. And the PMNS does something similar, but for neutrino mixing or oscillations as they're sometimes called. There are 2 key equations which can be derived from these terms, but I'll include them on screen anyhow for completeness. So one is the Einstein field equation, and the other is the Yang-Mills equation. Since the Einstein tensor on the left-hand side can be thought of as an operator that acts on the Riemann tensor, you can rewrite it into this form, Now I'm going to write both of these equations suggestively, as Einstein suggests, in a suggestive manner. If you squint, you'll see an analogy here between Yang-Mills and Einstein. Both theories involve operations acting on curvature tensors to map them back into field variables and sources. However, one huge difference is how these operators interact with symmetries. In Yang-Mills theory, gauge covariance is preserved under gauge transformations due to the structure of the covariant derivative and field strength. In contrast, the linear contraction operator, which I've denoted P, which is used to form the Einstein tensor, denoted G, in general relativity, doesn't commute with gauge transformations. I'll leave my proof of this on screen for those who don't believe me. You can just pause. But also, there are show notes in the description with a full breakdown of everything in this video. This, by the way, is partly what Eric means when he talks about the twin origin problems, but more on that later. In Yang-Mills theory, this involves Lie algebra-valued 1 forms, which are also known as the gauge potentials or connections, while in general relativity, it involves symmetric rank 2 tensors, or the metric tensor as you may know it. What other analogies exist? And how can we make these analogies not only precise, but derived? Furthermore, how can this be done with the smallest set of simple assumptions possible? That's what geometric unity aims to achieve. That was just a teaser. The link to the full 3-hour geometric unity iceberg is in the description, where I explain that theory from my point of view at various levels, for a PhD, for a graduate student, for an undergrad, and a general explain like I'm 5. Link in the description.